Okay, so good morning to all of you. The title of the work is Anti-eavesdropping Proportional Fairness Access Control for 5G Networks. So myself Shankar Kumar Ghosh, and I have done this work with my research group at Indian Statistical Institute, and myself from Presidency University, Bangalore, and I have also done my PhD from Indian Statistical Institute. So in this work, what we have done is we have developed an anti-eavesdropping proportional fair access mechanism, and anti-eavesdropping proportional fair access mechanism for fifth generation cellular network. So what we will do is, so first I will present the introduction and the motivation of the problem, then I will present the system model, then I will present our proposed anti-eavesdropping proportional fair access scheduling, then I will present the analytical framework that we have developed to analyze the performance of the proposed APF scheduling algorithm. Then I will present the results, and finally the conclusion portion will come. So recently, the applicability of new radio network, the radio access technology for 5G system, has been extended to unlicensed. And unlicensed suffers from several security threats like eavesdropping. So eavesdropping means the source is sending some information to the destination through the wireless medium, but due to the broadcasting nature of the wireless medium, that information is also delivered to some unintended receiver, which is known as eavesdropper. Now, due to malicious purpose, the eavesdropper may decode that signal. The eavesdropper may decode that signal. And that information may be available to the eavesdropper. So, and for that reason, what happens is that the secrecy throughput or legitimate user will degrade. So, secrecy throughput is defined as the throughput or the amount of data that is delivered to a legitimate user, which is not overheard by the eavesdropper. And also, it is quite difficult to identify the eavesdroppers because usually the eavesdroppers are passive, so it is difficult to detect. And for active eavesdroppers, some characteristics are there, but that characteristics should be known to the base station beforehand, and usually that characteristics are not known. So in this work, what we will do is we are attempting to develop one scheduling algorithm so that we can remove the eavesdroppers, so that we can defer the scale, we can remove or we can reduce the probability of an eavesdropper being scheduled by a particular base station. So then the eavesdropper, if we do not schedule the eavesdropper will not be able to consume resources from the base station, and accordingly the throughput will increase. So our contribution is we have proposed an anti-eavesdropping proportional fair access mechanism considering the possibility of eavesdropper. So the anti-eavesdropping proportional fair access technique first estimates a set of suspected eavesdroppers based on sleep mode information. Then it reduces the possibility of scheduling the set of suspected eavesdroppers by imposing penalties. And the penalty assignment here are based on past average throughput, current channel condition, and modulation coding scheme. And what we have done is we have done both, we have developed an analytical framework based on hidden Markov model, and we have also done simulation in order to confirm that our proposed APF technique outperforms the traditional proportional fair access mechanism in terms of anti-eavesdropping efficiency and secrecy throughput. These are the two performance metrics that we have considered. So we will introduce these performance metrics when we will come to that curve. So this is the system model that we have considered. So here one base station is there, one new radio base station is there, and we assume that the mobile terminals are uniformly distributed within the coverage region of the base station, and we consider that there exists a group of eavesdroppers that wish to decode secret messages. So see here U1, U5 and U6, these three users are legitimate users, and U2, U3 and U4, they are eavesdroppers. Now when the base station, at the current instant, the base station has a scheduled channel for U1 and U4. So U1 is a legitimate user. So when a signal is sent to the U1, then that signal is also delivered to U2 and U3, and as a result, that information is overheard by that U2 and U3, that means the eavesdroppers. On the other hand, this U4, that means this secret eavesdropper, that has also been scheduled, and this eavesdropper is consuming resources from the base station as well, and for that reason U6 and U5, these two legitimate users are starving. So that way the presence of eavesdropper is decreasing the secrecy throughput for the legitimate users. It decreases in two ways. First one is the legitimate user signal is delivered to the eavesdropper. So secrecy throughput means the actual throughput minus the throughput consumed by the eavesdroppers. So that way, when the eavesdroppers is listening, then the secrecy throughput is decreasing. On the other hand, when the U4, that means when the legitimate user is scheduled, then the when the eavesdropper is scheduled U4, then legitimate users U6 and U5 is starving. So in that way, the eavesdroppers are reducing throughput of the legitimate users. So what we have done is we have proposed a anti-eavesdropping proportional fair MAC access mechanism. This is a variation of proportional fair access, but here we have considered the possibility of eavesdropping, right? So here what we have done is we have first determined the set of suspected eavesdroppers based on sleep mode information, because we know that the eavesdroppers, even if they don't have any data, the receiver will be active. So when the receiver is active and it is receiving data, some leakage power will come from that receiver, and that leakage power can be detected by mobile terminals residing in close proximity. And that mobile terminals, these are trusted mobile terminals, they communicate the information to the respective base station, and the base station computes that what is the actual sleeping time for each and individual MTs. There we organize the mobile terminals in terms of their sleeping time, and we sort the mobile terminals based on in ascending order of their sleeping time, and we take the first epsilon number of MTs. So epsilon is the total number of eavesdropper in the network, that is we assume that it is known to the base station beforehand, and it is a very common assumption. So the first epsilon number of users we are taking, as an eavesdropper. So this is the set of suspected eavesdropper. Now once the set of suspected eavesdropper is determined, then what we do is we assign a penalty coefficient for each and every eavesdropper k, and that penalty coefficient is computed based on the past average throughput. That means the eavesdropper which has consumed more past average throughput is entitled for a big penalty. And to minimize throughput degradation, the serving base station should defer the scheduling of eavesdropper k in proportion to its past average throughput as well. And see here, for legitimate users the penalty coefficient is 0. Then the individual penalty comes. Now based on the penalty coefficient for each and every eavesdropper k, we are computing the individual penalties. So the individual penalty is pk into rk to the power alpha. So here the rkt represents the throughput based on the SINR, and pkt is the proportional. The pkt is the penalty coefficient, and alpha is the this modulation and coding scheme. This is the severity index based on the modulation and coding scheme. So capturing all these things, we compute the penalty for each and every eavesdropper for eavesdropper k. And see, for legitimate users this pkt is equal to 0. So for legitimate users there is no penalty. So this is the final assignment of resource block allocation. So here see, as I have already told you, this is the formula based on which we are assigning the resource blocks. So for legitimate users this part is 0. For legitimate user this PUT into RUT, this part is 0. But for eavesdroppers some penalty is there. So since for eavesdropper we have increased the past average throughput by adding penalties, the possibility of scheduling a particular eavesdropper reduces. But on the other hand, on for the legitimate users, we are not assigning any penalties. So the possibility that users, that means that legitimate users has more probability of being scheduled. So this is the formula based on which we are determining that which resource block we should assign to a particular user. Now we have analyzed our proposed anti-eavesdropping proportional fair max access mechanism based on a hidden Markov model based model, because based on the hidden Markov model based analytical framework, because we know that we do not know correctly what are the users which are acting as the eavesdroppers and what are the actual legitimate users. So what we want is, by using the sleep mode information, we want to reduce the probability that a eavesdropper will be scheduled by the base station. That probability should be reduced. So how much the probability is reduced, that we want to assess based on this analytical framework, and that analytical framework is based on hidden Markov model. So here we have only, so at the actual scenario, we have only two states. That means one is the legitimate user, another one is the eavesdropper. That means at any instant of time, the base station is either serving the legitimate user or eavesdropper, but we don't know it. What we know is we have some secrecy throughput, some observed sequence of secrecy throughput, and from that observed sequence of secrecy throughput, we want to assess whether it is coming from all L sequence. All L means, ideally we know that the base station should schedule only legitimate users. So given a particular observation sequence, what is the probability that it is coming from all L sequence? More the probability is, that means we are more closer to the all legitimate users. That means number of legitimate users that is being scheduled is increasing. So here we have assumed that the time interval is has n equally spaced time steps t1, t2, t3 to tn, and the observed sequence over the time interval is this secrecy throughput, and based on the observation sequence, observation likelihood has been computed in proportion to the secrecy throughputs. And the anti-eavesdropping efficiency is the probability of getting the observation sequence from a hidden sequence of all L. So this is the expression for the anti-eavesdropping efficiency for proportional fair access mechanism. These are the final expressions. I am not going into the detail. If you are interested, I can discuss. And this is the final expression for anti-eavesdropping efficiency for APF mechanism, our proposed mechanism. So please note that since we have ruled out some of the eavesdroppers, so the anti-eavesdropping efficiency in our case is better compared to that of the traditional PF mechanism. So let us come to the result. This is the simulation setup that we have considered, and it is based on the standard setup. So this cell radius, percentage of eavesdroppers, bandwidth, noise power, everything, it is as per the standard. And this is the main result that we have obtained. That means the anti-eavesdropping efficiency in our approach is much better compared to that of proportional fair access, because we have used the sleep mode information, which is thereby we can eliminate some of the eavesdroppers which the traditional proportional fair access cannot do. And similarly, the secrecy throughput is also increasing because we are keep on eliminating the eavesdroppers from our system, whereas the traditional proportional fair access can't do it. And also from simulation result, we have seen that the fairness in our approach is good compared to that of the proportional fair access MAC access mechanism when the traffic load is increasing. In future, what we want to do is, we want to capture the exact set of eavesdroppers, and we plan to employ the carrier frequency offset information. And for further characterization of eavesdropping behavior, we aim to deploy the random matrix theory to analyze the multidimensional CFO data. So thanks for your participation. If you have any question, kindly ask me.